Good morning, class. So today we're moving on to chapter 34, which is about electrical components. So before we jump into that, I wanted to just say good morning again and hope everybody staying safe and staying healthy, following the rules and all that good stuff. There's rumors that saying we'll be going back to normal in May. So I'll keep you guys posted on how that goes. But as of right now, we're going to keep doing what we've been doing. So let's get started on Unit 34, electrical components. So the objectives are determine the resistance value of a color banded fixed resistor, provide examples of where and how transformers are used, identify paper and film, electrolytic, ceramic, and mica capacitors, identify the different types of thermostats, explain cut in, cut out, and differential on pressure switches, test transformers and capacitors, list the difference between the different types of fuses, explain the difference between relay logic and solid state logic, describe how a silicone rectifier operates. So resistors. Resistors are found in many circuits. They are designed to allow for a measured resistance that can affect either voltage or current as calculated by using Ohm's law. As an example, a resistor could be used in an electrical test meter to limit the current flow. Fixed resistors can be made from nickel wire wound on a ceramic tube and then covered with porcelain. Smaller fixed resistors are made from mixtures of powdered carbon and insulating materials molded into a round tubular shape. So these are some resistors here. These are other different types of fixed resistors. These, and I'll go ahead and try to make that a little bigger. So these are resistors that you would find like on circuit boards and things like that. Not something that we typically work on in the field. This type of stuff is factory done. I mean, there are people who do that, who repair circuit boards, but that's not a common occurrence in our trade. We just replace the entire board. So anyway, capacitor types. So these are actually capacitors too. I know we're used to seeing the kind that I showed in previous videos, the motor capacitors, but these capacitors are also found on circuit boards. Again, not something we deal with a whole lot. Can be done. All you need is a soldering iron, and you just melt the solder on the back of the board, pull the old piece out, replace it. But again, that's just not something that that a lot of techs, including myself, really do. Once if the board is acting weird, replace the board. One of the reasons being is that we can't warranty those types of repairs. If we were to spend the time that it takes to fix a board and then and the board fails again, then the customer, like, you're just kind of opening up a whole can of worms, because now the customer is going to put it all on you, like, oh, you were the last one to touch it. Once the board is bad, it's bad. You can't provide any kind of guarantee on those types of repairs. So if you were to replace the entire board, for example, and the new board doesn't work, well, then you can just do a warranty exchange through the manufacturer. They'll replace the board for free. You can go back out and replace the board again. But there's no warranty for for repairs on an old board. You just gonna have to take the hit and go back and try to fix it again, or then try to swap out the circuit board after the fact. And it kind of, I don't know, sometimes depending on how you explain it, that could kind of affect your credibility, because they'll be like, well, why didn't you just do that in the first place? So anyway, but yeah, so anyways, these are capacitors. So not all capacitors are made of the same materials. There are paper and film, electrolytic, ceramic, and mica capacitors. Disc ceramic capacitors are commonly found on electronic circuit boards and are typically 0.1 microfarads or less. Mica capacitors are limited to even lower values than this. These are the capacitors that we are used to dealing with, the motor capacitors. Excuse me. So capacitors for motors are classified as either starting capacitors or running capacitors. When replacing a capacitor, it is desirable to use an exact replacement. Don't go over or under. You want to do it, give it an exact replacement. This means a capacitor with the same microfarad ratings and voltage limit ratings. Do not interchange start and run capacitors. Start capacitors are high capacity, 50 to 700 microfarads electrolytic units that are intended for momentary use in starting motors. They are normally encased in plastic. Run capacitors have a much lower capacitance rating, like 2 to 40 microfarads, but are made for continuous duty use. They are normally sealed in a metal can. Some run capacitors can have some sort of mark, usually a red dot, to indicate the terminal that should be connected to the run terminal. Excuse me. Transformer design. So this is an illustration of a transformer, but this one here, this is the kind of transformer you typically see in an AC unit. Then over here you have a variable transformer where you can change the voltage. So these the ones that we have like in class, they also have different voltage settings, but it's a matter of changing the wires, how you configure the wires. So transformers are constructed using the induction characteristics of AC power. When current flows through a coil, a magnetic field is produced. When a second coil is placed in the field of the current carrying coil, electric current can be transferred to the second coil. As an example, a transformer that has multiple primary taps could be connected for 120 volts, 208 volts, 240 volts, depending on the tap used. Variable transformers also allow for changing the voltage output. So yeah, so that's pretty much what I was saying. So the different taps that they're referring to are in actuality, like if you got the transformer in your hand, it'll be the different wires, different color wires. So your white, for example, would be your neutral. So that's a constant. But then you'll have a red, an orange, and a black. Your black would be your 120, your red would be your 240, and your orange would be your 460, or, for example. So if that's the case, then if you're using it on a 120 volt furnace, then you'll be using the white and the black wires. And then the red and the orange, you would cap those off separately, and those would just not be in use. But let's say you want to use that same type of transformer on a commercial package unit, and it's a 460 volt unit. Well, then you would have your white for your neutral, but then you would use your orange for your 460, and then your black and your reds will be separately capped off and set aside and won't be in use. So those are the different taps, basically just the different wires for whichever voltage is necessary for that unit. And then the other one, this variable one here, does the same thing, but you can just turn the dial. That is not one that I've actually used. I've always used these types, and the Versatech brand is actually the one I use the most. It just happens to be one of the more common brands. Transformer application and construction. There are many different types of transformers for many different applications. Large power transformers are designed to operate at electric utility voltages from 115 volts to several thousand volts. A common use for some smaller transformers is to provide low voltage AC to rectifiers for conversion to DC, which is direct current. These would be called rectifier transformers. Air conditioning systems use low voltage transformers to provide 24 volts alternating current to control circuits to operate relays and solenoids. These step down the voltage from the line voltage to 24 volts. and are referred to as control transformers. And so we kind of touched on that before, but basically, if you have a 240 volt condenser outside, you still need 24 volts to activate that coil. So basically, the 24 volts is what they say, which is your control voltage. That's what's gonna close and open your contacts. You have 24 volts going to your contactor coil, it's gonna close the contacts and allow the 240 volts to pass and energize the condenser. You take away the 24 volts from the coil, the contacts are gonna open, condenser is gonna cut off. And it's the same way with your heat or whichever mode you're operating. You have your control voltage, which is your 24 volts coming from your thermostat, and the signal coming from the thermostat is going to go to whichever component that you're trying to power up. And once it receives that signal, it's going to close some contacts, and then the line voltage will be allowed to pass and operate your system. So you got your line voltage and you have your control voltage. And the control voltage comes from the transformer. It's going to step it down to 24. So transformers will heat up during operation. This production of heat is inefficient. Transformer cores are made of thin sheet metal strips in the form of a laminate. There are a number of advantages to using a thin sheet metal strip. It is far easier to manufacture thin sheets because they can be stamped, where the thicker material would have to be cut. Also, the voltage induced in the core will cause the current called eddy current to circulate. One second. All right, moving on. So yeah, so these are those large transformers that you see outside, like on the phone poles. These are our controlled thermostat transformers, again, the kind that we have in our furnaces and our AC systems. And then over here is the rectifier. The straight eddy current flow through the transformer core is reduced by the oxide surface treatment of the laminations. That's just a little bit closer look at that. All right. So, go back. Fuses. Sorry, let me give me some water. I mean to keep clearing my throat all in your ear like that. So fuses, residential service entrance panel with the access cover open to provide access to the circuit breakers. So this is your breaker panel. I'm pretty sure we're all familiar with that. So your breakers kind of do the same thing that fuses do. They're overcurrent protection. So where the power comes into the building, it enters a service entrance panel for a distribution to the various electrical loads. Each electrical circuit that comes from this panel is electrically protected by either a fuse or a circuit breaker. A sample fuse and two commonly used fuse symbols are shown. A fuse is a special electrical conductor that is placed in series with the load and melts when excessive current flows through it, opening the circuit. Fuses are available in different types and sizes so that they can be selected to match the requirements for specific loads. So one thing I learned in the field, when you're putting fuses, so when I did my first install, I didn't know how to figure out what size fuses that system needs. It's pretty simple. It's on the data tag of the unit. It'll say maximum circuit amps, and it'll probably say like 30 or something like that. It changes depending on the size of the unit. But you want to use the size fuse that it requires. And inside that fuse, there's this little fusible link that'll melt when it heats up to a certain level, because electricity generates heat, and the more current, the more heat. So they have these things engineered to break at a certain level that indicates an overcurrent. So basically, if the fuse is rated for 20 amps, 21 amps will be hot enough to melt that link on the inside, blow the fuse, and cut the power to the unit, and to prevent any further damage. 21 is just an example. I mean, there's probably like a small tolerance, but basically when there's too much current flow, it's gonna blow the fuse, cut the system off to protect the load, because it's supposed to operate at 20. And if it's anything over that, you're gonna damage the motor. So rather than letting the motor get the overcurrent and burn out, we'll let the fuse burn out, and then you can investigate the problem, figure it out, make whatever repairs necessary, put your new fuses in, and then move on with life, without having to replace your actual motor or whatever the actual load is. So that's the whole point of a circuit breaker or a fuse. Circuit breakers and switches. All residences have some type of electrical panel where the electrical service enters the building and is distributed to the circuits in the building. Each circuit has some type of protective device to automatically disconnect the power in case the circuit is overloaded. This protection can either be a fuse or as described above, or a circuit breaker. Note the symbols used to represent a circuit breaker in an electrical wiring diagram. So that right there, that is your breaker symbol. You'll see that on your electrical diagrams. Switches can come in all shapes and sizes. They are often normally open when the switch position is changed from off to on. The switch contacts will close and energize a circuit, the same as when you turn on a light. Switches can also be designed to be normally closed, which de-energizes the circuit when the contacts are open. So a normally closed switch would be like your door switch. So on your furnace, so it's normally closed, and then when you take the door switch, when you take the panel off, the door switch will open up and it'll de-energize the system. But yeah, there's different types of switches for different reasons. And you'll see them throughout your system. You got safety switches, door switches. They all have their purpose. Switches. Proximity switches often limit motion and are often operated by the movement of a mechanical device. An example would be a switch that stops the motor used for opening air inlet dampers once they have reached a full open position. A typical residential safety switch is shown. Switches are rated by the voltage and current they can safely switch. Operating a switch on a higher voltage or heavier current than its rating is dangerous. Also, like fire hazard. Again, electricity generates heat. Overheat a wire, it'll melt that. It'll melt the insulation on that wire, and if it was to come into contact with something, it could ignite it. So definitely, it's a fire hazard. Low voltage thermostats. That's what we use typically in our trade. There are some 120 volt thermostats that I've dealt with before, but usually they're 24 volt low voltage thermostats. So low voltage thermostats have two manual switches, a system switch and a fan switch. The system switch controls the operating modes of off, cooling, heating. The fan switch controls the cycling of the fan. In the on position, the fan operates all the time, regardless of the thermostat setting. In the auto position, the fan cycles with the system. So auto means when the fan switches in auto, the fan will automatically cut on when you turn the AC on, or it'll automatically cut on when you turn the heat on. And if neither the AC or the heat is on, then the fan will be off. If you switch the fan in the on position, it's going to run constantly. So it'll be on during the cooling cycle if you got your AC going. It'll be on during the heating mode if you got the heat going. If you don't have the heat or the AC going, the fan will still just be going on its own, just circulating the ambient air, which some people do from time to time just to kind of what they call scrub the air, because when you're running your fan, you still have your filter in the return. So you'll be, just blowing, the air that you're blowing out won't be conditioned air. It'll just be the ambient air, but it'll be traveling back through the return and being filtered and then coming back out through the supply. So sometimes people will run the fan just to kind of, just to run the air through a filter, just to kind of clean the air in the house and just to get some circulation. So for many years, thermostats were electromechanical, using bimetal coils to move a mercury bulb switch. The bimetal element is composed of two different metals bonded together. As the temperature surrounding the element changes, the metals will expand or contract. Newer low voltage thermostats are now digital, using thermistors to sense the temperature and logic to control the operation of electronic switches and relays on the thermostat. They are not showing one. Oh, yes, they are. So these are pretty cool. Like when I first realized, how these old mercury bulb thermostats worked, it was actually kind of genius to me. So here's your mercury bulb thermostat, right? Let me see if I can get any closer. There's a small amount of mercury in there, and if you're familiar with mercury, it's like liquid metal. So it's just a little glob of liquid metal in there, and there's two contacts in there, on the heat side, and then there's two contacts on the cooling side. And so when you turn the dial, when you set the if you were to set the temperature all the way down for heat, then this mercury bulb would tilt toward the left, and then the two contacts will become closed because that liquid metal is a conductor. So once that little glob flows to this side, it'll close that circuit and bring the AC on. And then if you tilt the bulb the other way, meaning like if you were to set it the heat all the way to the right, then that bulb will tip the other way, and then the contacts inside will be closed with that same mercury on the other end, and now your heat is on. So it was just kind of dope to me how somebody figured that out. Like, oh, we'll just put a little bit of mercury in there, and then that'll complete the circuit depending on which way the bulb is tilted. So it was kind of cool, but it's very outdated, it's old, and also hazardous. So that ain't used no more. Everything is digital now. There are sensors and thermistors and stuff in your digital thermostats now, and we don't really have any use for that old technology. But it's cool to know how it works. Humidistats. Humidistats control the operation of their switches based on changes in humidity. Hygroscopic elements are used on these controls, including human hair. As the moisture content of the air increases and the humidity rises, the hair expands and allows the electrical contacts to close. As the humidity level decreases, the hair begins to dry. It contracts and once again activates the electrical contacts. This type of control is susceptible to dirt and dust in the air. A more common form of humidistat uses a nylon element instead of human hair. The nylon is bonded to a light metal in the shape of a coil spring. The expanding and contracting of the nylon creates the same effect as that found in the spiral bimetallic strip used in the thermostats. Another type uses a thin treated nylon ribbon as a sensor. So those are humidistats. Those are what you are what controls your humidifier if you have one installed in your system. Usually installed in like desert areas, places where it's really dry and hot. Pressure switches. Similar to a line voltage thermostat, a pressure switch uses a diaphragm or bellows to operate a switch. The difference in that, the difference is that the pressure operating the pressure operating the pressure switch comes directly from the refrigeration system. The pressure switch is either attached directly to the system or it has a capillary tube that connects the pressure switch to the system. So you can see both. So this is your pressure switch here, which is connected directly to your system, to your, looks like your liquid line. And then over here, this is your pressure switch. And the switch itself isn't directly connected, but it has this little cap tube that goes back and connects to the line on your system. In class, we've seen these. We got high pressure switches on our condensers in the lab. We don't have low pressure switches, which you'll find on a lot of units. They'll have both, but the whole point of it is to cut the power to the system when the pressure becomes excessive so that you don't damage our compressor. So on ours, we have these two little yellow wires. It's not blue like in this picture. Those yellow wires, some of you may remember, that connect to our contactor coil, that is coming directly from our pressure switch. What it does is it allows the current from the thermostat, our 24-volt signal coming from our thermostat that's trying to tell us to turn the condenser on, it'll go through that switch first and make sure the switch is closed. And then from the pressure switch to the contactor coil, then it'll allow that coil to energize, close the contacts, and turn the compressor on. But it'll only do that if the pressure switch is closed. If it's open, it ain't gonna allow it to run so that we don't damage the compressor. This one is a manual reset pressure switch where you could just hit this little button and the system will start back up. The problem with those reset ones, the one reason I don't like them is because people use it and get lazy. They'll just hit the button, system will come back on, they walk away, problem solved, I'm a hero, until the problem reappears and then it'll trip the switch again. So if you do find yourself having to reset your pressure switch, you're gonna want to throw your gauges on there and check the pressures out and watch and see how the system performs, because something caused it to trip and it'll probably trip again. But I've also had faulty switches that were tripping for no reason at all. And I had to bypass them. And I didn't just bypass it irresponsibly and not check the system. I ran the system for like an hour, like just kept doing all my simple little checks. So actually, well, I've done both. I've had times where I did have to make an adjustment and still had to bypass it. Then I've had times where there was no adjustment necessary. It's just a bad switch. And so anyway, if you bypass a reset, if you bypass the switch, you still want to just make sure your pressures are correct. And really, honestly, that's not something you want to do, but it's been done. And so these are different kinds of pressure switches. So many commercial refrigeration systems use both a close on rise, low pressure safety switch, and an open on rise, high pressure safety switch. Dual pressure switches combine the two switches into one mechanism. Adjustable pressure switches allow adjustments to the operating point and the differential. Adjustable pressure switches are often used on commercial refrigeration. Close on rise switches have an adjustment for the cut in and differential. The cut out is set by the cut in and differential. For example, a switch with a cut in of 250 PSI and a differential of 50 PSI would have a cut out of 200 PSI. So cut in just means basically the cut in or cut out, or no, let me backtrack. So close on rise means So close on rise is your high pressure switch. So once your temperature starts to rise above the cutout point, it's gonna cut your system off, because now your pressures are excessive and is in danger of damaging your compressor. And then the close on the close on drop is, I'm sorry, so when it opens on rise or when it opens on a drop, then that means when it opens on a rise, that means it's a high pressure switch. When it opens on a drop, that means it's a low pressure switch, because it's going to open up the circuit when the pressure gets too low. Or the same on the high, it's going to open up the circuit when the pressure gets too high. And those are adjustable. And here's another manual reset pressure switch. Air conditioning systems typically use small fixed pressure switches connected directly to the system. So, so yeah, you'll see these from time to time. Honestly, I haven't seen many manual reset switches on much newer equipment. I usually see that on the older stuff. Flow switches and solenoid coils. Flow switches open or close based on the movement of fluid. Note that both air and water are fluids. The cell switch is a protective device used to prevent the operation of a unit where there is inadequate fluid flow. Figure 3656 shows a cutaway of a solenoid valve. A solenoid valve is an electrically operated valve that controls the flow of fluid by opening or closing when the solenoid coil is energized. They may be either normally open or normally closed. When the coil is energized, the valve will change position. Normally open valves will close, or normally closed valves will open. Relays. An automatic switch requires some method of opening and closing. This is often accomplished through the use of a relay. A relay is an electrically operated switch that uses an electromagnet to open or close a set of contacts. So they operate pretty much like a contactor. And these are just different types. This is pretty old one. Well, you see these on some newer stuff. It just all depends on the equipment. But yeah, they operate pretty much like a contactor, where there's a coil. When that coil is energized, it'll cause the contacts to change position, whether it goes from open to closed or from closed to open. Solid state logic. Unlike relay logic, solid state components have no moving parts. They are sealed from the atmosphere. They take up less space because most of the components are attached to a compact circuit board. They generally cost less and require less power. Most importantly, they can be more than 1,000 times faster than relays. And so these are some solid state relays and a couple of different circuit boards. And again, you'll see all those fancy little, gadgets on your circuit boards, but we don't really bother too much changing all the, individual resistors, capacitors, and things like that. We just change out the whole board if necessary. But the boards, they're a lot faster. They send and receive signals way more efficiently than like an old school unit that doesn't have a board. It's just got a bunch of different relays and contactors. I have opened up some systems, some older package units, and just seen a whole bunch of relays and contactors and no board in sight. And I mean, they work fine, but you don't see that typically too much now with the newer stuff. There's boards on your package units, there's boards in your furnaces, and it just communicates the signals just a lot more efficiently. Transducers and solid state components. Transducers are electrical and electromechanical devices that are often used to provide a control signal. They can be used to sense changes in pressure, temperature, light, sound, and vibration. They are most often semiconductors that convert mechanical force into electrical signal. A diode is a semiconductor that acts similar to a check valve allowing for one-way flow through an electrical current circuit. A diode has an anode and a cathode, and so this would be your diode electrical symbol, and it allows current to flow in one direction and not the other. Common diodes. Diodes can vary from the size and pinhead, from the size of a pinhead to much larger sizes for ratings of 500 amps or more. Silicone rectifiers. Figure 3676A shows the current flow of a direct current meter through diode rectifiers, 3 and then 2. When the AC current reverses, the meter will still be operating on direct current with current flow through diode rectifiers 1 and 4. Silicone and silicone control rectifiers. Silicone rectifiers can be designed to operate throughout a wide range of current and voltage levels and are therefore used on many different types of applications. The SCR is similar to a diode in that it will block reverse current. The difference is that the SCR can also block forward current. More importantly, it can be switched electrically to allow forward current conduction by a pulse of current flowing through its gate. When the SCR is triggered by a gate pulse, conduction begins. An important application for an SCR is that it can be turned on and off like a switch without the need for electrical contacts. The speed of switching is also much faster than traditional contacts, and the timing can be varied during operation. A TRIAC is a bidirectional device of two SCRs connected in parallel, opposed with a common gate. A positive voltage applied to the gate will fire the TRIAC in either direction. So in summary, resistors and capacitors are commonly found in most circuits. Capacitors are used for many applications such as tuning, filtering, energy storage, power factor correction, and motor starting. Transformers have primary and secondary windings that can be configured to step up or step down the voltage. And fuses and circuit breakers are used to limit the current flow in a circuit to avoid overheating and fire. Switches, relays, and contactors are used to close and open circuits. And relays can be used in combination to start, stop, and engage safety cutouts. So that is unit 34, right? Yeah, 34. Unit 34, electrical components. So the review questions will be on FlexiQuiz. So study your book. Also review this video. Hopefully the two together will help you get through these review questions and the upcoming exam at the end of the week. So again, hope this was helpful. Hope everybody's healthy and safe. We'll see y'all on the next one.